everyone and welcome to Instant Biology by Dr. Neelab. Today we are going to talk about a very requested topic, and the topic is topoisomerases. Now for those of you who are more comfortable in Hindi, I have already made a video on topoisomerases in Hindi. You can go and watch that. But this particular video would be in English. I would be using a wire in order to explain to you that how a topoisomerase functions. I would also be talking about the classification and the mechanism of action of topoisomerases. Okay, so let us start the topic. What is topoisomerases and where does the reference firstly come? So if I'm talking about topoisomerases, we firstly find out this reference, or we firstly learn about topoisomerases in the process of replication. Okay, so what was replication? Basically, if I just give you an overview, in the case of replication, what did we do? We just replicated, or we just made copies of the DNA strand that we had. Okay, DNA is a double-stranded structure, and when we are making the copies of the DNA, then the process is called as replication. Now, in the process of replication, what happens is DNA helicase is an enzyme that is utilized for freeing the two strands. What do I mean by freeing the two strands? Breaking the hydrogen bonds between the two strands. So this is the function of DNA helicase. So if these are the two strands, these are present very close to each other, binded together with the help of hydrogen bonding, and when the helicase runs, the two strands are separated like this. So let me just show it to you with the help of a wire that I have. Now you can see that this is a wire, right? And this wire is having, this is a double stranded wire, you can say that. And one is black in color, the other one is red in color. So this resembles a double stranded DNA helix, right? If I talk about the process of replication, DNA helicase, what was the function of DNA helicase? DNA helicase function was to break the hydrogen bonds that were present between the red and the black strand, right? So when the DNA helicase was progressing in this way, what was happening is the hydrogen bonds were breaking, that is fine, but there was something like this. I mean, the strands were behaving something like this. You can see like that, okay? Now, what you can see over here is that a stress has developed over here, or a strain, you can say. The strain has developed over here. Why has the strain developed? Because of the movement of helicase. Helicase moves at a very fast speed. Helicase is going on breaking the bonds, and later on in the strand, or a later stage, or far away from this position, somewhere over here, you can see that a stress or a strain has developed. Now, this helicase would not be able to cross this strain. Until and unless this strain is removed, helicase would not be able to pass through this. This is a problem. And if helicase is not able to pass through this, then the polymerase that is coming from behind, it will also not be able to pass through this, or the replication will be halted. In other words, you can say that the replication will be halted. Now comes the functionality of topoisomerase. Now what does the topoisomerase do? Over here I have written that one more thing over here, this helicase I have shown over here. What is the function of helicase? Helicase is just breaking the bonds between the two strands, and it is creating positive supercoiling. So what do you mean by positive supercoiling? Now you can see that the strand over here, the two strands over here, look positively supercoiled. So what do you mean by positive supercoiling? Basically, when the strands become overwound, now there are two things, overwinding and underwinding. Overwinding means when the winding has enhanced because of the process, or because of the because of the mechanism, or because of the functionality of DNA helicase. What has happened is the positive supercoiling, or the overwinding, has increased, okay, and because of that the strain has developed over here. Now what is the process, or what is the function of topoisomerase over here? Topoisomerase sole function is to remove this strain, so that the replication that was previously halted, it can start once again. So this is the functionality of topoisomerase. So all in all, what have I said? Topoisomerase releases the positive supercoiling due to DNA unwinding. Now what does the topoisomerase do? topoisomerase, I will be talking about the mechanism in detail in the upcoming portion, but what I want to say over here is that the functionality of topoisomerase is to just release the stress over here. And how does the stress, or how is the stress released? By unwinding the DNA strand. Remember, I just said that helicase is causing the overwinding, and overwinding results in positive supercoiling. But what is the functionality of topoisomerase? Topoisomerase is causing unwinding. Okay, it is causing unwinding, and unwinding results in the negative supercoiling. I will be talking about that in just a moment. Okay, so up till here you would have understood that topoisomerase is just an enzyme that will cause the unwinding of the DNA strand and to release the strain that is caused by helicase, right? So next, let us talk about very popular topoisomerase. Now this topoisomerase is asked in most of the examination. So what is the name of this topoisomerase? In case of prokaryotes, the major topoisomerase is DNA gyrase. Sir, what is this DNA gyrase? DNA gyrase is an example of type 2 topoisomerases. Now what are these type 2 topoisomerases? I will talk about type 2 over here. Okay, so just remember for now, just understand this, that a DNA gyrase is a type of a type 2 topoisomerase. You don't have to remember anything else. Next, which topoisomerase is the most common in case of eukaryotes? So in case of eukaryotes, topoisomerase 1b is the most common topoisomerase. We will be talking more about this also. Now, what does DNA gyrase and topoisomerase 1b do? So they will release the positive supercoiling by introducing the negative supercoiling. So this is just the same thing that we had spoken about over here. What does the DNA gyrase or topoisomerase 1b do? They just release the positive supercoiling by introducing the negative supercoiling. Positive supercoiling was introduced by DNA helicase, and this positive supercoiling is undone or released by introduction of negative supercoiling by the topoisomerase. And what topoisomerase is? DNA gyrase, which is an example of type 2 topoisomerase, and eukaryotes have majorly type 1b topoisomerase. Now remember, this is the most common one, and this is asked in most of the examinations. That is why I have written down a few points about DNA gyrase. You should be knowing about this. Let us just briefly talk about DNA gyrase. So what is DNA gyrase? DNA gyrase requires ATP hydrolysis, and then only it will be able to function. What do you understand by ATP hydrolysis? Simply it requires ATP to function. Okay. So DNA gyrase will require ATP to function. Next is, it is a heterotetramer. What does hetero means? Hetero means that there are different subunits, and there are 4 subunits in total. That is, in total we call as heterotetramer. Now what are the subunits of this DNA gyrase? There are 2 subunits, basically gyre A and gyre B. Now there are in numbers there are gyre A 2 subunits and gyre B 2 subunits. That is why we are calling it as heterotetramer. Okay, now what is the functionality of gyre A and what is the functionality of gyre B? This is important. Gyre A, what will it do? It will cut and rejoin the DNA, and gyre B, what will it do? It will provide the energy. Now let us understand this once again. Let us talk about gyrase. Okay, what about gyrase? So as I said, that DNA gyrase, what will it do? It will release the positive supercoiling by introducing the negative supercoiling. So how would you introduce the negative supercoiling? So what is done is, I'll just explain it to you. So suppose these are the 2 strands. Okay, suppose over here in this region, let us say in this region, over here in this region, there is the strain that has been developed because of DNA helicase. So what will DNA gyrase or any other topoisomerase will do? I'm just giving you a brief explanation. I'll be talking about major mechanism over here. What will be done? What is actually done? Suppose it is topoisomerase 1. Suppose it is topoisomerase 1. Then what will happen? One of the strands will be cut. Suppose this strand is cut. And after cutting, what will happen? The strand that is uncut is passed over the strand that is cut. Suppose I make a cut over here. red one. So the black one will be passed over the red one so that the strain can be removed. Okay, because of this, when the other strand passes over the cut strand, the strain becomes removed, and in this way what you are doing is you are entering, or you are providing the negative supercoiling, and because of this you are relieving the positive supercoiling. So this is being done. So I'm just telling you, what does gyre A do? Gyre A cuts and rejoins the DNA. So if I take the example that one strand is being cut, so if this strand is being cut over here, and after cutting, what is happening is that the other strand will be passed on and then it will be rejoined. Okay, which subunit will provide the energy for this? Gyre B subunit will be providing the energy for this. Why? Because I have already said that it will be utilizing ATP for this entire process. One more thing, as I have already said that the DNA gyrase is type 2 topoisomerase. Therefore, DNA gyrase will be cutting both the strands. But for simplicity, for your understanding now, I will be talking about the cutting of both strands later on. But for simplicity, for your understanding now, I just gave you the example of cutting one strand. In originality, DNA gyrase will be cutting two strands. Okay, I believe you would have understood. And remember, gyre A would be responsible for cutting and religation, cutting and resealing of the strand, whereas gyre B would be responsible for providing the energy. Now, again, a very important concept comes into being is about inhibitors. Antibiotics are one of the most important things that are asked in GAT B, GAT B and CSIR NET examinations. You should be very well aware that which of the antibiotics are inhibiting gyre A as a subunit and which antibiotics inhibit gyre B. Let us talk about this. That quinolones antibiotics, so quinolone antibiotic, example is nalidixic acid, and derivative of this quinolone antibiotic, that is fluorinated derivatives. The example is norfloxacin and ciprofloxacin. So fluorinated derivative of quinolones is norfloxacin and ciprofloxacin, and normal quinolone antibiotic is nalidixic acid. So all of these three antibiotics, they inhibit gyre A subunit. Now again, what does the gyre A subunit do? It cuts and then religates the strand. What about gyre B subunit? Is there any other antibiotic that can inhibit gyre B subunit? Yes, the name of the antibiotic is novobiocin. Novobiocin is the name of the antibiotic. So I believe you would now have a clear idea about the inhibitors of this DNA gyrase. Now let us talk about the mechanism of action and classification of topoisomerases. Firstly, topoisomerases are examples of nucleases. What does a nuclease do? Nuclease will be able to cut nucleic acid. Okay, so the function will be cutting a nucleic acid. Now, when I'm saying cutting is a very generic term. Which bond is broken over here if I talk about that? It is the phosphodiester bond. Not only the bond is cut, but it is religated also, as I already have explained in case of gyre A. So, because it is a nuclease function is to cut the strand, and then after cutting it religates also. In all this process, a phosphodiester bond is broken. Now, what is phosphodiester bond? Phosphodiester bond is a COPOC bond. If you don't know about this, I'll just briefly explain it to you. When one nucleotide is connected to another nucleotide during the formation or during the process of replication, what happens is a phosphodiester bond is formed. The 3' OH of a sugar, deoxyribose sugar, it attacks on the 5' phosphate, and the bond that is formed is called as a phosphodiester bond. Now this phosphodiester bond is broken up by the nuclease. Okay. Now let us come to the portion where we can classify the topoisomerases. Now topoisomerases can be classified for the purpose of easier understanding into two parts: type 1 topoisomerases and type 2 topoisomerases. Now what is the difference between those? Type 1 topoisomerases will cleave only one DNA strand and pass the other strand through the break, and after that resealing is done. Now what do I mean over here? Suppose I am talking about topoisomerase 1. In case of topoisomerase 1, what will happen is, suppose these are the two strands, right? And over here the strain is present, over here the strain is present. So in case of topoisomerase type 1, one strand will be cut. So a cut will be produced like this. This strand will be cut and the other strand will be passed through the break. So this red one will be passed through the break and then it will be resealed. This is the concept of type 1 topoisomerase. Now again you would have an idea that why this is done. This is again done to relieve the supercoiling. Now if I talk about type 2 topoisomerase, what is type 2 topoisomerase? It will cleave both the DNA strand and pass another double strand through the break. What do I mean? Now if I'm coiling this again and again, look at this. Now you can see that this is supercoiled on itself. Can you see this? I believe you would be able to see this. What has happened is this portion has supercoiled on itself. Now I am holding this portion only. Okay, so this is the condition over here. This is the condition over here, right? So one DNA strand, one DNA is just crossing over onto the other DNA. This is the example of supercoiling. What I want you to understand over here is that the type 2 topoisomerase will cut both the DNA strands. It will cut both the DNA strands and then pass another double strand through the break. So what will happen? If suppose I want to resolve this structure, so what will I do? I will cut both the double strands over here. What will I do? I'll cut both the double strands over here, and then this strand would be broken. What will I do? The other strand that is behind this, I will pass this back strand through the forward strand, and I'll then release this supercoiling. I'll release this string. So in this way, what is the major difference? The major difference is in type 1 topoisomerase, only one strand is broken. In case of type 2 topoisomerases, both the strands are broken and one DNA is passed through the other DNA. So passed through the break and then after that again it is resealed. So this is the major difference between type 1 and type 2 topoisomerases. I've seen students getting confused in this. So you should have a clear idea about this. One more important concept is what is the way in which the naming has been done of type 1 and type 2. In case of type 1 topoisomerases, odd Roman numerals are used. For example, the examples of type 1 are topo 1, topo 5, things like that. Okay, but if I'm talking about type 2 topoisomerases, even Roman numerals are required or even Roman numerals are used. Okay. Another difference is that over here no ATP is required. That means type 1 topoisomerases does not require ATP for its functionality. But there is an exception to this. The exception is reverse gyrase. Sir, what is reverse gyrase? Just like gyrase, what was gyrase doing? If you remember, gyrase was introducing negative supercoils so that the positive supercoils produced by the DNA helicase can get nullified. But reverse gyrase, what will it do? It will do the reverse functionality of the DNA gyrase. Okay, so what will it do? It will produce positive supercoils. Okay, so I believe you would have understood that it will create positive supercoils. Now, if it creates positive supercoils, it definitely needs to have certain ATP or utilize ATP, only then it will be able to do this. Therefore, reverse gyrase will be requiring ATP hydrolysis. Other than this reverse gyrase, all the type 1 topoisomerases do not require ATP hydrolysis. Do not confuse this reverse gyrase with DNA gyrase. Remember, DNA gyrase was an example of type 2 topoisomerase. But I'm just giving you an analogy, I'm just giving you a way to learn that reverse gyrase will have a functionality entirely opposite to the DNA gyrase. The functionality was DNA gyrase was producing negative supercoiling in order to neutralize the positive supercoiling created by DNA helicase. But this reverse gyrase, what will it do? It will create positive supercoiling. For that, it will require ATP hydrolysis. Now, let me talk about type 2 topoisomerases. Type 2 topoisomerases also do not require ATP for cleavage and religation. Remember, for cleavage and religation, no ATP will be required. but ATP is required for conformational changes in the protein. Only for conformational changes ATP is required. Other than that, over here also, just like type 1 topoisomerases, ATP is not required. Now, let us talk about the mechanism. How does a topoisomerase function? Let us discuss about that. So, all topoisomerases utilize nucleophilic tyrosine. Sir, what do you mean by nucleophilic tyrosine? Now, in order to understand what is nucleophilic tyrosine, first of all, you should have a clear-cut idea about what is tyrosine. Tyrosine is an amino acid, okay? And this is an amino acid which has a OH group. Tyrosine and serine are OH containing amino acids. Now, so what is the phenomenon? What is the role of this nucleophilic tyrosine? Remember that all topoisomerases have tyrosine in their active site. Now, with the help of this tyrosine, since I have already said that the tyrosine has a OH group, with the help of the OH group, what does it do? In one case, or it can attack on the 3 or the 5 prime phosphate in one case and 3 prime phosphate in the other case. Let me just explain it to you in a better way. See, all the topoisomerases will have a nucleophilic tyrosine. You would have understood this. Now the oxygen of the tyrosine, again I am talking about the OH group, the oxygen of the tyrosine will break the CO-POC bond. Which bond is this? This is the phosphodiester bond that we have talked about over here. So it will break the phosphodiester bond and create a phosphotyrosine bond. So how this is created, how a phosphotyrosine bond is created, let me just explain it to you. That type 1 topoisomerase is of two types, type 1A and type 1B. I have explained the functionality of type 1A over here and type 1B over here. So what does type 1A do? How does type 1A function? So this is a double-stranded DNA, you can see, and this double-stranded DNA is acted upon by the OH group or tyrosine containing oxygen, okay, or the oxygen of the tyrosine. So where does the tyrosine oxygen attack in case of type 1A? What happens is the 5 prime phosphate is attacked and a phosphotyrosine bond is formed. So you can see over here, on this phosphate tyrosine is attached. This is called as a phosphotyrosine bond and this is created in type 1A topoisomerase. Let us talk about type 1B topoisomerase. In type 1B topoisomerase, what happens is that the 3 prime phosphate group is attacked upon by the tyrosine. So over here, the 3 prime phosphate, on the 3 prime phosphate, the tyrosine is attached. This is the functionality of type 1B. Now let me enhance upon whatever I have said. So type 1A topoisomerases function with the mechanism of strand passage mechanism. What is the mechanism called as? Strand passage mechanism. What is this mechanism? One strand is cleaved and the second is passed through the gap. So over here you can see that one strand is cleaved, that means this black one has been cleaved, and the red one is passed through the gap. So red one will be passed through the gap. So if this was the strand, red one will be passed through the gap. This is the concept of type 1A and the name that has been given is strand passage mechanism. Let us talk about type 1B. One more thing. Type 1A topoisomerases will change the linking number by 1. What about type 1B topoisomerases? It will just relax the supercoil. It will cause a relaxation of the supercoil and one DNA strand rotates with respect to the other. Over here what is happening? One DNA strand, so this DNA strand will be rotating like this. So I have drawn this also. It will be rotating like this with respect to the other in case of type 1B topoisomerase. And remember that it can change the linking number by any integer, not unlike this type 1A which was able to change by 1 only. Okay, so what are the examples of type 1A? Type 1A's examples include topoisomerase 1A, example is in eubacteria. Topo 3, example is in eubacteria and eukaryotes. That means this topo 3 functions in eubacteria and eukaryotes. Reverse gyrase that we had just talked about over here. Reverse gyrase is functional in eubacteria and archaea. Type 1B, if I talk about this one, type 1B does not have any other examples. It has only one member in its family. Let us talk about type 2 topoisomerases. I've already explained how type 2 topoisomerases function. You already know that it will break the double-stranded DNA and it will form a covalent linkage to both the strands. That means phosphotyrosine will be formed or attached to both the strands. Now, that double-stranded break in one DNA, the DNA in which the double-stranded break took place. So if you remember, I had created something like this. Now, if the double-stranded break is created in this strand, this one will be called as G segment. The double-stranded break in the DNA, double-stranded break in the DNA, that DNA is called as G segment, and the other segment that is passed, so this one was the one in which the cut was created, and the one that will be passed through the gap is called as the T segment. So you should be knowing the names of these segments, G segment and T segment. Okay, now these topoisomerases 2 will change the linking number by 2. Coming to the classification of type 2 topoisomerase and examples, type 2 topoisomerases can be said as type 2A topoisomerase and type 2B topoisomerase. Examples of type 2A topoisomerases are as follows: topo 2 in eukaryotes, topo 4 in bacteria, DNA gyrase in archaea over here. The examples of type 2B include topo 6 in plants and homologs of SPO11. Now these function with the duplex strand passage mechanism. Duplex strand passage, what does this mean? Duplex strand passage means both the two strands of the DNA are cut and then one strand is passed. This is called as duplex. Duplex because two strands are involved. Over here, strand passage mechanism because only one strand was present or one strand was cut. So I believe you would have got a clear-cut idea about the classification, about the mechanism, about DNA gyrase, about reverse gyrase. I've explained a lot of things over here, and this lecture would be pretty important if you are an aspirant of life science examinations or biotechnology examinations. So I hope you would have liked this video. If you've liked this video, please hit the like button, subscribe to my channel, please hit the bell icon, and do not forget to share it with your friends. Thank you so much. Have a good day.